Well, hello everybody. I'm Michael Seary and I'm the Director of Teaching here in the School of Chemistry, and I'm also a Professor of Chemistry Education, and I'll be taking you for this final course on thermodynamics or chemical thermodynamics. That's the final part of Chemistry 1A and Chemistry for Chemical Engineers 1A. And in this course we'll be looking at essentially thermodynamics or energy transfer, all kinds of considerations about energy. And the way this course works is that you'll have a set of lecture notes that are sort of gap notes that you'll be able to fill in as you're watching these videos. And these lecture notes really aim to be your primary source of information for the lecture. So these should be the things that you build your lecture notes on, using the videos, using what you learn from textbooks, and so on. So in this course, what we'll be doing is essentially asking three core questions. The first is quite a big core question. It is what is energy? What do we mean when we talk about energy? And I suppose especially in the context of chemistry, why do we want to think about energy at all? And obviously the answer is obvious. Energy and energy considerations underpin pretty much every chemical process, every chemical consideration we can think of. The second consideration, I think, or the second question is how do we quantify energy, or how do we quantify, I suppose, the transfer of energy more importantly. And that for me is what makes chemical thermodynamics quite an interesting subject, because it's about experimental science. It's a sense of finding out and figuring out how do we measure the amount of energy transfer in a particular chemical reaction. And the third reaction, or the third question, is looking at why do chemical reactions proceed. And that's a pretty deep question, and that'll bring us on to the second law of thermodynamics and looking at energy distribution, looking at what's called reaction spontaneity, and so on. And that will wrap up the course, because that will give us an overarching consideration of a chemical reaction. Why does it proceed energetically, but also what is the fundamental driving force making a reaction proceed? And we want to be able to answer a question: if we have two chemical substances, will they react? Okay, so as I mentioned, you'll have student handouts, so these will be available on Learn, so you can fill these in pen and paper if you want to print them out, or there'll be Word documents, so you can feel free to type in. And really the aim here is to give you a concise set of notes that you'll be able to use for reviewing this topic and for revision. There'll also be PowerPoint notes, so you'll be able to use PowerPoint notes if you want to go over these slides again. There will be the last weekly quiz of the semester, you'll be glad to hear. That weekly quiz is a little bit different because the questions are numeric, so therefore everybody will get a different question. And then there will be the final tutorial of the series will be on thermodynamics. Alright, so in this first lecture I wanted to introduce thermodynamics as a topic, as we are doing, but also focus on two aspects. I wanted to focus on considering what energy is from a chemical point of view. How do we describe energy? And as you'll see when we get to that, that's the second part of this lecture. It's a little bit vague in a way, perhaps a little bit unhelpful even, but we need to have this sense of what energy is before we can move on to the much more useful considerations of energy and energy measurement in the next couple of lectures. So this first lecture is really getting a sense of how much energy are we talking about, and where is that energy coming from. And also we'll be introducing from the start of this lecture and throughout issues around changes in energy, because really that's what we're obsessed about in thermodynamics. When a chemical reaction proceeds, something is changing, so therefore what is the change in energy in that chemical reaction? Okay, so thermodynamics is a pretty old subject. In fact, I'm sitting here recording this in the Joseph Black building, and it was Joseph Black arguably who started off thermodynamics, because before Black, people didn't really understand what heat was. So there was a sense that maybe chemical substances, so this is in the 1700s, chemical substances had some kind of inner fire in them, which I suppose philosophically you could consider. Some other people thought that heat was a chemical element in its own right. So there wasn't a good understanding of what heat was. And Black did a lot of experimentation. So Black obviously is famous for discovery of carbon dioxide, but he did a lot of experimentation relating to heat and temperature. And he was one of the early pioneers in really distinguishing our understanding of what heat was, in terms of we now know that as a form of energy, but also what temperature was, and the difference between heat and temperature. So heat being the amount of energy that that a substance has, for example, due to kinetic energy of molecules. Temperature being the measurement of the temperature of a substance. And Black's experiments, such as looking at melting ice and the temperature of melting ice, and not changing until all of the ice melted, led us to now what we now commonly know as latent heat. He also looked at the fact that different substances absorb different amounts of heat when we heat them up. So this is what we now consider in terms of specific heat capacity and so on. So he really got us going. So I'm sitting in my office, and just outside my office is a plaque to Joseph Black. So that's probably appropriate. So thermodynamics as a discipline, I suppose, then comes from that. Thermo meaning heat, and dynamics meaning movement or change. And Black's work really focused on this idea of energy change. And that really, from that time, powered a major revolution in consideration of energy as a source that we can use for good. And no more so than the internal combustion engine. And here we see in the internal combustion engine a fuel coming into a cell, and the fuel will be ignited in this cell, and when it's ignited, that fuel will combust, and as it combusts, it'll spit out lots and lots of gas in the form of carbon dioxide and water, and that gas then will expand, so it'll push this piston down, and that piston will drive a wheel around and move the car forward. This is pretty traditional, pretty old school thermodynamics, but we can see here a fuel is coming in, a chemical substance is coming in, and it's reacting, and that is then causing some energy change, energy transformation. So that fuel, the potential energy, is being pushed into work, and that work is pushing at the piston and driving something forward. There's also a whole area of thermodynamics underpinning biochemistry and biochemical reactions, and every human being, every biological being needs energy to make it function, and at very intricate levels. So here we have a very common energy source in the body, adenine triphosphate, ATP, and that liberates a phosphate, so that gives to ADP, so it liberates one phosphate group to give adenine diphosphate, and this spits out an amount of energy. And that energy will power something nearby. So it'll power, for example, in this cartoon, sodium and potassium ions going through particular channels in the body. So very similar to here, where we have some fuel doing some work. Here we have some fuel pushing these ions through the body. And it's the same considerations are present. And in many ways, society, we're coming around again to a consideration of these core energy concerns that were there before the Industrial Revolution, because now as humankind, we need to think about where our energy is coming from in the future, and this is not yet a problem that has been solved. As our population grows and more people are plugging into a grid, we need better and cleaner energy sources. So a lot of work, and this is just a cartoon taken from work that Professor Pullum does here with a Scottish company here in Edinburgh, where they're looking at clever ways of heat transfer between materials of different types, and those materials will be able to absorb different amounts of energy, and they will release them as needed. So we're going back to the very basics, really, that Black conceptualized in terms of heat transfer and in terms of heat capacity. So this is very modern work, currently being researched. So there's a lot of scope for understanding energy and how we capture and manage change in energy for research in the future. All right, so to get us going, I thought we'd just have a look at this video. It'll just take a second to get started. All right, so that the sigh of relief at the end there of the demonstrator. Glad that the reaction has gone okay. That's called the screaming jelly baby reaction. And what we can see is a jelly baby, in other words, a source of sucrose, high sugar content substance, has been added to some powerful oxidizing agent, something like potassium perchlorate or something like that, the liquid in the test tube. So this is now essentially a combustion reaction. Remember, combustion is reaction of an organic substance to form carbon dioxide and water. And what can we see here? Well, we can see lots of transformations. We can see a gas has been given off. So this is likely steam due to water being produced. Remember, combustion produces water. So at the temperatures that this reaction is currently at, that water will be vaporized. So we're seeing steam being given off. Obviously, we're seeing a lot of light due to the heat of the reaction that it's reaching. We're hearing sound. So the physical substance, if we were to go to the end, the physical substance here, we see some black soot. So that's probably incomplete combustion of the carbon. So there's lots of transformations going on here. And our job in thermodynamics is to think of the energy transformations. So what I want to do is just talk through essentially a chemical reaction and what that means in terms of energy transformations. So we can draw out a diagram or a figure where we can represent the energy of carbon dioxide, the sucrose, C12H22O11, as a solid, and that's going to react with oxygen. And that will form some product. And here we know that combustion will form carbon dioxide and water. So if you look here, we have 12 carbon dioxide, so that must mean we need 12 sucrose, carbons in our sucrose, so that must mean we need 12 carbon dioxides. We have 22 hydrogens, so that must mean we need 11 waters. So that gives us 33 oxygens on this side. We've already got 11 here, so I need 11 to give me 22 oxygens here. What's happening then? So we add our sucrose to this highly oxidizing source. What's happening? Well, obviously, a chemical substance, if it is stable, doesn't just start reacting. Okay, so that substance will have a lot of energy, but it's not going to just start reacting. It'll need something either to react with, or it'll need some energy that it's going to initiate the breaking of all of the bonds. So the first step that has to happen is provision of energy to this substance. And this provision of energy goes towards breaking the bonds in the molecule. So all of those carbon-carbon bonds, all of those carbon-hydrogen bonds must break. We know they must break because there are no carbon-carbon bonds in the products and no carbon-hydrogen bonds in the product. So all of those bonds are being ripped apart as they are breaking. So where is this energy coming from? Well, likely in this reaction is coming from the very strong oxidizing agent that is our oxygen source. So this is really important because very often we talk about substances having energy and that they will just suddenly break apart. That is true. Substances are sometimes very unstable, but they will always need even a little bit of energy to overcome some barrier to go and form products. That must be the case, because if that wasn't the case, they wouldn't exist in the first place. All right, so we always have this uphill energy, no matter how small or big it is, for a reaction to proceed. And that will form some intermediate state, where this molecule is broken apart and there's all kind of fragments sitting there, and they can rejoin and go back and form products, or obviously they can go on and they can form, they can rejoin and go back to form reactants, or they can go on and form products, and they will do so by making new bonds. And what we have here then is essentially a reaction profile diagram. And this reaction profile diagram here, we will just for the moment draw energy on our y-axis. That will change. We'll get more nuance as the course goes on. We'll keep coming back to that y-axis and changing it. And on the x-axis, we tend to call this something like reaction profile. It's not always time, because it depends on where the reaction is. So this is essentially the journey that the reaction will take in going from reactants to products. And what we are interested in thermodynamics is this energy gap here. This delta E, sorry, I've gone a bit too far there. This delta E between the reactant energies and the product energies is the amount of energy that transfers as a result of this chemical reaction. And that is what thermodynamics is about. All right? In kinetics, in other words, how fast chemical reactions go, they look at this energy gap here, the difference between the reactants and this intermediate or transition state. Because obviously the higher that gap is, the more energy a reaction will need to overcome that bump, so therefore the slower the reaction will be. In thermodynamics, we are interested in the difference in energy between starting materials and products, or what we call the initial state and the final state. So everything that we are obsessed with is what is the energy of our reactants, what is the energy of our products, and what is the difference between the two of them. And if that difference is positive, in other words, the energy of the the energy of the products is higher than the energy of the reactants, well then that will be a positive energy difference. That means the system will need energy to be put into it to make the reaction proceed. If it's negative, in other words, our value here is lower, our final value is lower than our initial value, well then that means the system has given out energy, just like the screaming jelly baby reaction we had. So we are all about measuring this delta E value. So here we have our diagram here, just written out again. So we are breaking reactant bonds initially and then making product bonds. And this gap that we have here is the value that we are measuring. We can see here that I've written in states, and this is really important in thermodynamics. Okay, so I've written in my solid, my gas given off here. Here I've written water as a liquid. Now we could see steam being given off here. All right, so clearly water as a liquid isn't in its liquid form here. But what this reaction is representing is the overall journey of this reaction from start to finish when all of that water has condensed. And that's an important distinction to note experimentally. All right, you must think about, well, what am I looking at experimentally, and therefore what is the energy of the system as I look at it compared to what is the energy of this system as I'm representing it in a chemical equation. So what's happening to this energy? Well, we can talk about our reaction again, and now, as I said, we're interested in, well, how much energy is going in or out of that reaction. And we quantify this or describe this in terms of system and surroundings. So a system is the chemical system that we are looking at. So for example, what's going on in this test tube. So I'll just put a box around this diagram to indicate the energy considerations in there are all within the system, and then if they leave the system, in other words, heat passes through the walls and goes onto my hand if I'm holding the test tube foolishly, or this gas, this work that's being pushed out, well, that is energy leaving the system, and it is going to the surroundings. So in thermodynamics, we talk about systems and surroundings. This is the energy that we are looking at within our system. Is that energy being passed out to the surroundings, or is the surroundings pushing energy into the system? And this idea of accounting, this simple way of allowing for accounting of energy, is based on the law of conservation of energy, which says that energy can neither be created nor destroyed, but only transferred from one form to another. And Feynman, who is a famous physicist, wrote some very elegant lectures, and this is a quote from one of his lectures that says the same thing about the conservation of energy. That is a most abstract idea, because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is just a strange fact that when we calculate some number, and when finish watching nature go through her tricks and calculate the number again, it is the same. It's a very, very elegant quote, I think. But it's essentially saying that we can use this way of accounting for energy because energy is conserved. The total amount of energy does not change. How can we account them? What could we measure? If you were to look at this chemical reaction and go, well, how would I get a sense of energy transfer here? What could you do? So have a think for a moment. What kind of things could you measure in that chemical reaction to get a sense of the energy transformation that is happening? All right, so if we look at this, we've got heat here. Heat is this reaction is glowing. There's so much heat coming off. So if we were to immerse this in some kind of calorimeter and measure the heat transfer to, for example, water in the surroundings, and measure the temperature increase in that water, I'm sure you've all done that experiment. Well, then we'll be able to get a sense of the heat that left this chemical reaction and passed to the surroundings. We could also measure the pressure being given off due to the gas evolution, and that would give us the amount of work, energy transfer due to a pressure change that was being given off. Okay, so we will be able to measure lots of ways: temperature change, pressure change, volume of the gas being given off, even mass of the substance changes. That would give us some sense of the chemical reaction that's going on. There are lots of experimental ways that we can measure energy transfer. Obviously, some of these ways might be restricted depending on the type of chemical reaction that is going on. Okay, so this idea of systems and surroundings just needs a little bit more refining. So when we talk about systems, there are three types of systems we can have. The first is the one we've just been looking at, this open system. And this is where matter and heat can exchange with the surroundings. So gas can enter or leave this chemical system. Heat can pass through the walls of the flask. In a closed system, well, it's stoppered. So now heat can still pass through the walls of the flask, but matter can't escape. And an isolated system is one where both heat and matter are held within the system. So we can't have any energy exchange in or out of the isolated system. So therefore the amount of energy that's in that system, because of the law of conservation of energy, never changes. The form of it may change, but the amount never changes. And we call this kind of system where heat can't pass through, we call those adiabatic. Adiabatic means heat can't pass through the walls of the system. All right, so I mentioned that we're interested in this idea of energy transformation. So we want to know, well, how much energy was in our products, in our reactants, how much energy is in our products, and therefore what is the difference between them. What I wanted to move on to now is think about, well, what is this energy? When we talk about energy, what is it? Why does a chemical substance have energy? Okay, and this is the part of the lecture where we have to sort of go a little bit abstract and just think about these considerations almost conceptually, and then we'll bring it back in the next lecture to something much more tangible and useful that we can measure. But it is important, I think, to understand when we talk about energy and amounts of energy, where that energy is coming from. And the first type of energy is what's called potential energy. And many of you in physics will have come across this. This is a stored energy, or an amount of energy something has just by being. So this could be energy stored in chemical bonds or in the nucleus, or for more than one molecule, the energy in intermolecular forces and so on. Remember, when we talk about energy stored in chemical bonds, that doesn't mean that chemical bonds just suddenly have all this energy that they can make for a reaction to proceed. We must still provide molecules that exist with energy for a reaction to proceed. Otherwise, they wouldn't exist as molecules in the first place. So this is just the energy stored in the molecule due to all of those nuclear electron repulsion, attractions, and so on that are in the molecule. And we can get a rough sense, and this is really just an approximation of what kind of energies we're talking about here by using mean bond enthalpies. So I'm sure you've come across these in previous studies, and this essentially says, well, if we were to take a molecule like methane, CH4, and we were to completely decompose that, the amount of energy involved in completely decomposing that would be 4 times each carbon-hydrogen bond. So we'll be able to work out what the energy, or the mean bond enthalpy, and I'll come back to this term enthalpy in the next lecture, what that energy is. And we can see here this is pretty considerable. Alright, so even though it's an approximation, we can see that these energies are in the hundreds of kilojoules per mole. Okay, kilojoules per mole is our energy unit here. So this is a pretty substantial amount of energy. So no wonder when we pump fuel into our car engine, fuel is octane, C8H18, and combust it, there's a hell of a lot of energy in there for every molecule for every mole of octane. So the potential energy is a massive source of energy within molecules. The second type of energy is kinetic energy, and this is energy due to the movement of the molecules. So this is energy due to translation, in other words, movement in the x, y, or z direction. Rotation, in other words, rotation of the molecule through space. Okay, so rotation means we are moving molecules through space. Or vibration, in other words, the movement or vibration of molecules relative to each other. And this kinetic energy is also a source of energy. It's also contributes to the amount of energy a substance has. It's obviously a little bit more difficult to quantify. And a way of quantifying it is to think about the energy due to movement. So if we look at, for example, a monatomic atom. Well, this monatomic atom, what can it do? It can move in the x direction, it can move in the y direction, and it can move in the z direction. So it can move in 3 different directions. So therefore, this has what we call one particle has 3 degrees of freedom. So degrees of freedom are ways in which it can move. So any movement that's somewhere between, for example, x and z is a combination of x and z. So therefore, we say there are 3 distinct degrees of freedom. What about something that has 2 atoms? Well, obviously, again, that can move in the x, y, and z direction. So there are 3 translational degrees of freedom. It can rotate. Okay, so it can rotate around the, let me just label these again. I'm going to call this one z-axis this time, y and x. Okay, so the z-axis is the axis of the bond of the molecule. So if that rotates around the bond of the molecule, well then the molecule isn't rotating through space. We are not moving molecules through space. So that is not a degree of freedom because it doesn't involve any kinetic energy. But we can move around the x-axis, for example. So to move around the x-axis would mean this would rotate around this way, so we'll be moving back into the plane of the board and out again. And we can move around the y-axis, in other words, we'll rotate around the plane. So this has 2 rotational, so there are two atoms here. And obviously this molecule can vibrate, so the 2 atoms can vibrate relative to each other, so we've got 1 vibrational. So this molecule has 6 degrees of freedom. All right, and what we find here is that the number of degrees of freedom is equal to 3n. So here we've got 3 degrees of freedom, here we've got 6 degrees of freedom. What about a triatomic molecule? Well, a triatomic molecule again will have 3 translational. It'll have 2 rotational, okay, because again rotation around the z-axis is not moving molecules through space, so it'll have 2 rotational, and it'll have how many vibrational? Well, it'll be able to vibrate several ways. So I'll show you some examples for the moment, but if we know that the total here is 3 and we know the total must be 9, that must mean there are 4 vibrational. And I'll show you an example now of what those different vibrational modes might look like. That was for a linear triatomic. For a non-linear triatomic, well, now suddenly rotation in any direction will involve moving molecules through space. So again, this has 3 atoms, but now it has 3 translational, 3 rotational, and therefore now only 3 vibrational, with a total of 9. So we can see here, this is the summary of that diagram. And what this is telling us is, obviously the more degrees of freedom a substance has, the more it can move. The more it can move, the higher its kinetic energy. So we use degrees of freedom as an approximation or a guide to giving us a sense of kinetic energy of a molecule. And I mentioned there are different vibrational modes. So let me just open up here what these vibrational modes might look like. So here we see all kinds of different vibrational modes. So when we count vibrational modes, and this is something you'll take up in spectroscopy next year and the year after, there are lots of different ways molecules can vibrate, and each of those will have their own energy, and each of those will appear somewhere in this case, infrared spectrum. All right. So as I mentioned, we have 3n degrees of freedom, usually for always for translation there are 3 degrees of freedom. For rotation there are 3 degrees of freedom, rotation in the x, y and z axis, or 2 if there's only a linear molecule, and for vibration, well, it'll be the remainder. For non-linear it'll be 3n minus 6, the 3 from translation and the 3 from rotation. For linear it'll be 5, 3n minus 5, the 3 from translation or the 2 from rotation. So this allows us to calculate now for a molecule. We get a sense for the larger this molecule is, the more n, the larger the n value, the number of atoms, the greater the kinetic energy. So how do we quantify that kinetic energy? Well, we use something called the equipartition theorem. And the equipartition theorem allows us to calculate an average energy for each degree of freedom a molecule has. So for every degree of freedom that we've calculated here, we'll be able to say, well, that individual degree of freedom contributes to the overall kinetic energy using the equipartition theorem. And this relies on something called the Boltzmann constant. And the Boltzmann constant, Boltzmann looked at distributions and energy distributions in molecules. So we use this value here, the Boltzmann constant, 1.38 by 10 to the minus 23 joules per Kelvin. And this is telling us that for every increment in Kelvin, this value will contribute 1.38 by 10 to the minus 23 joules, a very small amount of energy. And what that means is that for every degree of freedom, we would just multiply those numbers of degrees of freedom. So for example, this molecule here, water, has 9 degrees of freedom. So we would say every molecule of water has 9 times the Boltzmann constant times the temperature the water is at, joules of energy. Obviously, sometimes we like to work in moles, so we can just relate the Boltzmann constant to the gas constant. They're essentially the same. They're just related by Avogadro's number. And now we get the equipartition theorem, but now it's in units joules per Kelvin per mole. So therefore, we can say that a mole of molecules has a half times the gas constant times temperature for every degree of freedom. All right. So what I'd like you to do is just take a pause in the video for a moment and work out what is the average energy per degree of freedom at this temperature for a single molecule and for a mole of molecules. So we can say for a single molecule, we've got, so it's a half kBT. So for each degree of freedom, okay, we're not told how many degrees of freedom the molecule has, so for each degree of freedom, it's a half times Boltzmann constant, joules per Kelvin, times the temperature that we're at, and we're at 298 Kelvin. So we can just scratch out the per Kelvin and the Kelvin, and that will leave us with units joules. And I get, when I do that, 2.06 by 10 to the minus 21 joules. Tiny, tiny amount of energy for each degree of freedom the molecule has. For a mole, well, now it's a half times RT, because we multiplied by Avogadro. So this is a half times 8.314 joules per Kelvin per mole, multiplied by 298 Kelvin. So again, we can scratch the Kelvin and the per Kelvin. So that gives me 1239 joules per mole. So for each mole of substance, the kinetic energy that every degree of freedom provides to that substance is 1239 joules per mole. So compare that with potential energy. It's much smaller, isn't it? Remember, the potential energy, every bond had hundreds of kilojoules per mole. Here we have 1 kilojoule per mole effectively for every degree of freedom. So naturally, the amount of kinetic energy a substance has is much lower than the potential energy a substance has. But nevertheless, it does make an appreciable contribution to the overall kinetic energy. Okay, so there are those calculations, and the important thing here is we're distinguishing between joules and joules per mole. So that means, as I mentioned, we just basically calculate for the numbers of degrees of freedom. So here for water, we would multiply this number by 9, and we would say, well, that is the kinetic energy that water has at 298 Kelvin. All right, let's wrap this up into a kind of a summary. We've said now that our chemical reaction has our reactants and our products. And I want to think about this energy change in terms of potential energy and kinetic energy. So if we were to make some kind of stacked plot, okay, so here I'm making a stacked plot, and I might put up here my how much potential energy and kinetic energy my reactants have, and how much potential energy and kinetic energy my products have. Well, obviously, Here my reactants have one very large molecule and 12 gas molecules. So we might expect here that the amount of potential energy, this sucrose molecule will have a huge amount of potential energy, lots and lots of chemical bonds here, massive amounts of individual bonds, each of them carrying their own mean bond enthalpy. So this is very rough, this is not to scale or anything, but this is just indicating that these reactants will have a very high potential energy. Alright, and sometimes you write in our y-axis here, if you remember I wrote energy, sometimes you write that as potential energy, simply because it's predominantly, the amount of energy in our system is predominantly potential energy. But nevertheless, there's going to be some kinetic energy here due to the vibrations in the sucrose, but mostly due to the movement of the gas. What happens when we get the chemical reaction? Well, now suddenly we've lost the massive amount of potential energy that this system had in the sucrose, because it's now all been combusted. And again, this is not to scale, but this just indicates, well, the amount of kinetic energy is dramatically increasing. We are losing a lot of potential energy, so the amount of kinetic energy is increasing. Now obviously this is not a closed system. Okay, our screaming jelly baby was able to release energy in the form of heat and work to its surroundings. So actually we shouldn't draw a stacked plot, we should just pile them up here like this, and the difference here will be the amount of energy that's lost to the system. And all of this discussion about potential energy, kinetic energy, is really just to show you what a pain in the neck it is to think in those terms. It is almost impossibly difficult to quantify how much energy a substance has. It is very, very difficult. You've just seen there, we can kind of get a good guess with mean bond enthalpies, and we can kind of try to work out using the Equipartition theorem. It's very messy. But what we can do very easily is not measure the amount of substance something has, but measure change. We can measure change very, very easily. So we can call this total amount of energy a substance has the internal energy, almost impossible to measure, in fact, possible to measure. But what we can do is measure the change in internal energy. How much does the internal energy differ from reactants to products? And that change is really easy to measure. We can easily measure heat output, we can easily measure work output. So thermodynamics in the very first instance now, the very first change we're going to make on our y-axis is we're going to change this y-axis now and call it internal energy. And therefore the change in internal energy from here to here, if you remember we called that delta E earlier on, now we can make that much more specific and call it delta U, where delta U is the change in internal energy. And our first few lectures are going to focus on this, because the exciting part of thermodynamics is we can measure that very easily. Alright, so that's just essentially summarizing. It's a bit of a pain to think about energy in terms of potential energy and kinetic energy. It is important we know that, because that kind of crops up again and again in various aspects. But in terms of actually thinking about energy change in terms of numbers, it's much easier to think about change in internal energy. And what we can do, if we go back to our diagram, is we can think about that change in internal energy in terms of heat and work, because that is how pretty much all energy is transforming. So we can measure the heat output of a chemical reaction, and we can measure the work, or more specifically the work of expansion, the work that this gas is doing in expanding from the reactants to the products. So it is very easy to measure, as we'll see in the next few lectures, heat, and it is very easy to measure work. And if we go back to our idea of an isolated system, we said the law of conservation of energy says the energy in that isolated system is constant. That's actually effectively what we call the first law of thermodynamics. The internal energy of an isolated system is constant. We can't move energy in and out of this system, so therefore it must remain constant. And we can use a version of that idea by saying, well, if energy can move in and out of this system, well then that energy difference that's moving in and out must be equal to the change in internal energy. So the mathematical statement of the first law essentially says the change in internal energy is the amount of heat that's left the system or gained by the system, plus the amount of work that's left the system or gained by the system. And we say left the system or gained by the system because the sign of that will be positive or negative depending on whether it's entering or leaving the system. So this allows us now very easily, we don't have to worry about potential energy, kinetic energy, all of those considerations. Now we can just very easily measure the heat and work input or output of a system. Alright, I'm going to leave it there. There are some review questions you might want to try. You just want to review some of the concept of this lecture, and I'll post the answers up on Learn, and I will catch up with you in the next lecture.